All right, how we doing? Today we're going to be learning a little bit about binary and hexadecimal. Okay, so binary, as you know, is a base 2 numbering system, and there are only two numbers in the binary. It's 0 and 1. A 1 or a 0 is called a bit. They get the word bit from the term binary digits, right? 8 bits together equals 1 byte. Now, what makes a byte significant is the smallest unit that can make a character in a computer. So 1 byte of information can be the letter A or the number 2 or whatever. Also, it's significant that we use binary with only two numbers because computers, specifically processors or CPUs, uses transistors. And transistors are switches with no moving parts. So a switch is either on or off, representing a 1 or a 0. 1 is on, 0 is off. I mentioned it has no moving parts because anything mechanical, anything that moves can wear out. But because transistors have no moving parts, they switch based on electrical impulses. They can go on and off a million times a second and never wear out. That's why your phone, you can use your phone for years, your computer for years. You can jostle your laptop around and nothing breaks because there are no moving parts in there, right? So for binary, every character or digit or color or everything that's on your screen is first converted to binary, right? And there's a code called ASCII that every computer in the world uses to represent certain characters. So this is the ASCII table, and the capital letter A is represented by this binary number, where the lowercase a is represented by this binary number. Now, ASCII is very popular. Again, it's universally used, but it's specifically for English. Unicode is a similar naming scheme, but it has more than 120,000 different characters. ASCII, because it only uses an 8-bit code, can only have up to 255, or I guess 256 if you count 0, different characters in it. It's limited, right? Where Unicode can have so much more. And Unicode is used on every computer in 129 different languages. So Unicode, you'll see that it's more universal than ASCII, all right? So again, a bit is either a 1 or 0. A byte is 8 bits together, which makes up the smallest unit that a computer uses to create a character. A kilobyte is 1,024 bytes. Now, sometimes, depending on what you're talking about, we often kind of round it down to 1,000. The same with megabyte. A megabyte technically is 124 kilobytes, and a gigabyte is 1,024 megabytes. But sometimes we round it down to 1,000, depending on what component we're talking about and what it is. So you have to kind of be aware of that. Other file sizes, a nibble. Yes, there is something called a nibble. It's actually half a byte, which means it's 4 bits. You got kilo, mega, giga, terabyte, which is kind of where we are right now. Kind of the next sizes up that you'll be seeing in the few years is petabyte, exabyte, zettabyte, yottabyte, brontobyte, and geobyte. This brontobyte is kind of fun. It used to be called something else. I forget what it is. It had another name, but they changed it to brontobyte a couple years ago, named after the brontosaurus, which is supposed to be the largest dinosaur, right? So that's kind of a small, fun little thing. ASCII, we talked about, it's the coding scheme that every computer in the world uses, but it's limited to 8 bits and 255 characters. Unicode is a more, it's a larger coding scheme that, and on this, guys, it says 120. I've seen different numbers on this, to be honest with you. I've seen it's more than 140 characters. I've seen 65,000 characters. I've seen over 1 million characters. So I think probably depends on how they define it, is the number of characters used. But what you need to know is it's used worldwide because Unicode addresses other languages, right? Hex, if you're familiar with that, is short for hexadecimal, and that is the 16-base numbering system, which we'll talk about here in a minute. Okay. So again, as I kind of mentioned, ASCII uses 1 byte of information to store 1 character, which is, again, 255 possibilities. Unicode uses 2 bytes to store 1 character, which that's where I'm getting these 65,000 plus characters it can have. Okay. So a byte of information. So this lady is holding 1 byte of information in 1945. I believe this was the ENIAC computer. Those big things there that look like light bulbs, they're called vacuum tubes. And that is what signified the on or off, or 1 or 0. The problem with these vacuum tubes is, just like a light bulb, they broke. They overheated and would burn out. So there was a constant issue with keeping the ENIAC running, because vacuum tubes, and if just 1 vacuum tube broke, the entire computer would be offline. But again, today we can see 1 terabyte of storage can fit on devices that are very small, right? These are both solid state drives. So let's get into counting. We count in base 10, and we call it base 10 because it's based on the powers of 10. So 10 to the 0 is 1, 10 to the first is 10, 10 squared is 1,000, 10 to the third is 10 squared is 100, 10 to the third is 1,000, and so forth. And so we use these groupings, right, based on powers of 10 to come up with our numbers. So this 16,743 is really saying I have 1 group of 1,000. I have 6 groups, I'm sorry, 1 group of 10,000, 6 groups of 1,000, 7 groups of 100, 4 groups of 10, with 3 left over. Okay? So in base 10, how do we say 8? We're saying 8, we don't have any groups of 10, we just have 8 individual things left over. 12 is saying we have 1 group of 10 with 2 left over. 158 is 1 group of 100, 5 groups of 10, 8 left over. 1,625 is 1 group of 1,000, 6 groups of 10, 6 groups of 100. I'm having trouble talking right now. 2 groups of 10, and 5 left over. All right, sounds easy enough. You learned that in 1st grade. If you understand how decimal works, you'll understand how binary works, because it's the same way. In binary, it's based on powers of 2. The groupings are based on powers of 2. So we have 2 to the 0, which is 1, right? The single things left over. 2 to the first, which is 2. 2 squared, 4. 2 to the third, 8. 16, 32, 64, and 128. These are the groupings we'll use. And notice I have 8 groupings here, because that makes up a byte of information. So 1 in decimal is also 1 in binary. 2 in decimal is 1, 0. 1 group of 2 with 0 left over. 3 in decimal is 1, 1. 1 group of 2 with 1 left over. 4 in decimal is 1, 0, 0. 1 group of 4, 0 groups of 2, 0 left over. Okay? So for 10, we say 1, 0, 1, 0, because we have 1 group of 8, 0 groups of 4, 2 left over. And the way you do this, guys, in your mind, the rhythm you're doing is, okay, how many times does 8 go into 10? 1 time. What's left over? What's 8 or 10 minus 8? 2. How many times does 4 go into 2? 0. How many times does 2 go into 2? Once. What's 2 minus 2? 0. How many times does 0 go into 1? 0 times. Okay. Same with 15. How many times does 8 go into 15? 1 time. And then 1 group of 4, 1 group of 2, and 1 group of 8. And guys, you do this by, if you add up all the slots that have 1 next to it, it should equal your number. So 8 plus 4 is 12, plus 2, is 14, plus 1 is 15. So that's how we get that, okay? 16 is one group of 16 with nothing left over. 20, it's one group of 16, right? Because we can't put a group of 32 in a 20, but we can't put 16 in a 20. What's left over? 4. So we have one group of 16, 0 groups of 8, one group of 4, 0 groups of 2, 0 left over. 16 plus 4 is 20. Okay? So hopefully you have the kind of the rhythm there. Go ahead and pause the video if you want and see if you can convert these numbers to decimal, and then I'll come back and I'll show you the answers. I mean, these decimal numbers, convert them to binary. Then we'll come back and show you the answer. All right, let's take a look. So 28 is 11100. 37 is 100101. And again, if you add up 32, because it's got a 1 in it, and 4 is 36, then you add up one more, and that's 37. 42 is 101010. 55, 110111. Okay? Now there's a shortcut method for figuring out converting decimal to binary. We'll show you what that is. So you take your number you want to convert. In this case it's 30. We want to convert that to binary. Then you take the next group up. So in this case it's 32. So what group is higher than 30 is 32. So 32 minus the number 30 gives us an answer 2. You take that answer, subtract 1 from it, and you take the results, which in this case is 1, and put zeros in the spot that add up to 1. So in this case, everything has a 1 in it except the one that has a 0. Okay? Let's do another example. We want to convert 58. So the next group up from 58 is 64, right? 64 minus 58 is 6. We take that answer, 6, and subtract 1 from it. We get a 5. We put zeros in the spots that add up to 5. So 4 and 1 equal 5. So we put zeros there and 1 everywhere else. So it's 111 and 010. So if you add up all the 1s, it'll be 58. And if you add up the zeros, it'll be 5. So if you like that method, you can use it. If you want to use the other method, it's up to you. Go ahead and pause the video and see if you convert these to binary. Then I'll come back and show you the answers. All right, let's take a look. Here's 61. And again, pause the video anytime if you want to kind of compare your answers to what I have on the screen. I'll just kind of scroll through and let you see what the answers are. All right. Hopefully you're getting these lower ones are kind of easy, you can do in your head, but as the numbers get higher, you might want to use a calculator, right? And it's okay for you to use a calculator on the quiz or the worksheet or anything you do when you're converting here. You don't want to make a simple math mistake. So again, pause the video, convert these, come back and I'll show you the answer. All right, here we go with the answer. Here's 125. That should be a 0 there. I don't know why that didn't show up. 133. 148. Right? Think you're getting good? Well, let's challenge you a little bit more with higher numbers. Again, pause the video and I'll show you the answers. All right, here's 150. 166, 172, 189. And this is our last group of binary, decimal to binary. If you haven't been doing the other ones, guys, go ahead and do these because these have some special meaning, which I'll explain here in a minute. So go ahead and convert those, pause the video, and then I'll come back and I will show you the answer. All right, let's take a look here. So 196 is this. Now for 240, 240 is kind of a special magic number. when we talk about computers, it's because of the way it converts to binary. The first four numbers are ones. The second four numbers are 0. So you'll see this in subnet masking and other kind of special situations because of the way it converts to binary. Right? Then 255 is the highest number you can have in 1 byte of information. They're all ones. Right? And then in order to go up one more decimal number to 256, we have to go from 8 groupings to 9 groupings. So 128 times 2, right, is 256, right? So that's the next group up. So I have one group of 256, 0 left over, right? But you don't see this much in binary. However, not to confuse you, you will see 256 from time to time when we're talking about hexadecimal. And we'll cover that here in a second, okay? Now, guys, you might, from one time or another, have to convert larger numbers to to binary. So if you have to, you just use that shortcut method. So if we want to convert this number to binary, you take the next group up. So the next group up from that is 2048, right? Subtract the number you're looking for to convert. You get an answer, which is 25. You take 25, subtract 1 from it. That's 24. Then you put zeros in the spots that add up to 24. So 16 plus 8 is 24. So I got zeros there, ones everywhere else, right? And then you can, same thing with 10,500. The next group up would be the 16,384, right? Subtract the number we're looking for, and we get 5,084. Subtract 1 from that, and put zeros in spots that add up to 5,883. And I know, I understand this is a little more complicated here, but you can see if you add up all these spots that have zeros in it, it'll come to 5,883, and then ones in all the other spots, right? Now, I mentioned the largest number in Unicode is 65,535, and I got that because Unicode uses 2 bytes of information, and the largest number you could have with all ones and 2 bytes of information is 65,535. I know this looks a little off balance, but I had to kind of give a little more room to these numbers down here because they're bigger numbers, and I squeeze these in tight. But you can see there's 8 spots here and 8 spots here, and this is 2 bytes of information. Okay. You also see that 65,000 is another kind of a special number that you see pop up. Most people will see it on the internet when they're looking for different colors to use. There's 65,535 different colors you can use that the most web browsers would recognize on the internet. Why? Is because they use 2 bytes of information. Okay. Now, binary is really hard for humans to kind of look at and convert in their head, but it's easy for computers. Base 10 is really easy for humans to look at and understand, but it's harder for computers to convert, right? So hex or hexadecimal is kind of a compromise where human beings can figure it out pretty quickly and computers can kind of deal with it. And we work hex the same way as we do binary and decimal. The groupings are based on powers of 16 because it's base 16. So 16 to the 0 is 1. 16 to the 1 is groups of 16. 16 squared is 256. There's that 256 I told you about, right? And then 16 to the third and 16 to the fourth, okay? So how does this work? How do you count in binary? Well, the top row is how we count in decimal, right? This is what we're used to. The bottom row is how you count in hex. So 1 through 9 are the same. 1, 2, 3, 4, 5, 6, 7, 8, 9. When we get to 10, we don't have a group of 10 or a group of 16. So we represent 10 with the letter A. We represent 11 with the letter B. 12 is C. 13 D. 14 E. 15 is F. Then when we get to 16 for hex, we have one group of 16 with 0 left over. So 16 in decimal is 10 in hex. One group of 16, 0 left over. So 8 in decimal is 8 in hex, right? 12 in decimal, if we go down here, 12 is C in hex. 15 is F. 16 is 1, 0, or 10. Okay, let's see how you guys do with these. So 20 in decimal, I have one group of 16, right? With what left over? Well, it's 20 minus 16, 4. So 14 in hex is 20 in decimal. Again, we have one group of 16, 4 left over. 33 in decimal is what in hex? Well, how many times does 16 go into 33? I got this little cheat sheet up here you can use. 16 times 2 is 32. So 16 goes into 33 twice. What's left over? 1. So it's 2, 1, 21. Two groups of 16 with 1 left over. For 45, we have two groups of 16. And what's left over? Well, what's 45 minus 32? 13. How do you say 13 in hex? D. So it's 2D. Okay. 56, we have now 3 groups of 16 because 16 times 3 is 48. What's left over? 8. So it's 3, 8. Okay, go ahead and pause the video, see if you can kind of go through these, convert these to hex, these decimal to hex. Use the cheat sheet at the top to kind of get that first number. Okay. All right, let's go through and take a look at these. So 61 is 3 groups of 16 with 13 left over. 78 is 4 groups of 16. 4 groups of 16 is 64. All right, what's left over? 14. How do you say 14 in hex? E. 89 is 5 groups of 16 with 9 left over. 95 is 5 groups of 16 with 15 left over. Okay, go ahead and convert these numbers here. Pause the video and then come back and I'll show you the answer. All right, let me scroll through these. So 100 is 64. 6E, 6 groups of 16 with 14 left over. 7B and 8A, 8 groups of 16 with 10 left over. Okay. Now there is a shortcut method to help figuring out converting decimal to hex. And it has a couple steps, but it's some people really like it, so I want to show you here. So the first thing you do is you have to convert your decimal number to binary. So 44 decimal, this is 44 in binary, 101100. At the top here, I've given you the groupings, right? And so then you change those groupings and you split it into 2 groups of 4. So you got the first kind of nibble of information, four bits, and then you split it and you start over again, right? And with 4 bits. Then you convert those independent nibbles into numbers. So here, this is 1 group of 2, 0 left over, it's 2. This is 1 group of 8, 1 group of 4, gives us 12. 12 in hex is C, so the answer is 2C. Okay, let's do a different one. We want to convert 110 to hex. So first we want to convert 110 to binary. So here's our groupings, right, in binary groupings. This is what 110 looks like in binary. Notice I split it into 2 nibbles or 2 groups of 4. Then I reordered the groupings to start over again after each 4 characters or digits. Then we convert those numbers. So 1 group of 4, 1 group of 2 is 8. Then we got 8, 4, and 2 is 12, 13, 14. So, oh, I'm sorry, did I say 8? I'm sorry, I'm not having a good day today, but I apologize. Stick with me. So 4 plus 2 is 6, and 14. So the answer is 6, and then how do you say 14 in hex? E. So the answer is 6E. So 1/10 of decimal is 6E in hex. And you could almost do that in your head if you're good in math. And if that's easy for you, go ahead and keep doing that. If not, you can do it the other way. Doesn't matter. Go ahead and pause the video. See if you convert these final numbers here to hex. I've helped you out by converting them to binary over here. So you can kind of figure it out in your head and with the groupings. Remember, you start over, 1, 2, 4, 8, 1, 2, 4, 8. Right? All right, let's take a look here. 149 is 95. Then we have CA. 230, or E6. FF, because remember, this is the largest number you could have in 1 byte of information, and so it's FF. Then if you go up 1 more to 256, you've got to go over again to the 9th spot, and so we have 1 group of 256, 0 groups, or 0 left over, right? 0 groups. All right, well, there you go. That's a quick way of going through. Whoops. Yeah, you don't need to do that. I've already done that for you. Okay? So, if you have any other questions, you're still kind of shaky on this, you're welcome to come and see me, and we'll help you out. Once you get in the rhythm, it's not hard to do. It is important for you to be able to convert or understand how to convert these numbers, at least up to 255, 256. Because that will help you with networking and other situations. All right. Good luck to you.